Welcome to the fascinating world of thermodynamics. This branch of science explores how energy, heat, and work interact and transform within our universe. From the tiniest atoms to massive engines, thermodynamics governs the rules that shape everything around us. In this video, we'll journey through the fundamental laws that explain why your coffee cools down, how engines power cars, and even how living organisms survive. Whether you're curious about nature or technology, understanding thermodynamics is key to unlocking the mysteries of energy transformations. Let's dive in and discover how these laws impact both the natural world and human innovation. Thermodynamics is the science that explains how energy moves and changes form. It deals with concepts like heat, work, and the flow of energy in physical systems. Imagine a pot of water boiling or a car engine running. Thermodynamics helps us understand what's happening inside. Key ideas include the system and its surroundings, energy conservation, heat transfer, and efficiency. By studying these principles, we can predict how energy behaves in everything from chemical reactions to power plants. Thermodynamics isn't just theoretical, it's the foundation for many technologies that power our modern world. Story of thermodynamics is filled with brilliant minds and groundbreaking discoveries. In 1798, Count Rumford revealed that heat is a form of energy through his cannon boring experiments. Then in 1824, Sadi Carnot published the principles of heat engines and introduced the idea of maximum efficiency. By 1850, Clausius and Kelvin formulated the second law of thermodynamics, forever changing our understanding of energy flow. Later, in 1909, Max Planck connected the third law to quantum theory. These milestones laid the foundation for modern science and technology, shaping how we harness and use energy today. Zeroth law of thermodynamics might sound mysterious, but it's essential for understanding temperature. It states that if two systems are each in thermal equilibrium with a third system, then they are in equilibrium with each other. This principle allows us to use thermometers to measure temperature accurately. For example, when you use a thermometer to check your body temperature, it reaches thermal equilibrium with you, ensuring the reading is correct. This law forms the basis for all temperature measurements and is the starting point for exploring more complex thermodynamic laws. First law of thermodynamics is all about energy conservation. It tells us that energy cannot be created or destroyed, only transformed from one form to another. The mathematical expression delta equals QW shows that the change in a system's internal energy equals the heat added minus the work done by the system. This law is fundamental to understanding how engines run, how our bodies use food, and even how the universe evolves. Every time energy changes form, whether it's chemical to mechanical or electrical to thermal, the total amount remains constant. Thermodynamics isn't just for scientists, it's everywhere in daily life. Take refrigerators, they remove heat from inside and release it outside following the first law's principles. Human metabolism is another example. Food energy is transformed into work and heat, powering our bodies. Car engines convert chemical energy from fuel into mechanical work and heat through combustion. These everyday examples show how energy transformations are guided by the first law, ensuring that energy is always conserved, no matter the process. Second law of thermodynamics introduces the concept of entropy or disorder. It states that heat naturally flows from hot to cold, and the entropy of an isolated system always increases over time. This explains why ice melts in a warm room and why engines can't be perfectly efficient. The Kelvin statement tells us that no heat engine can convert all heat into work, some energy is always lost. The Clausius statement adds that heat can't flow from cold to hot without external work. These principles set the direction for all natural processes. Heat engines are devices that convert heat into work, but their efficiency is always limited by thermodynamic laws. The Carnot engine represents the most efficient theoretical heat engine, setting the upper limit for what's possible. Its efficiency depends on the temperatures of the hot and cold reservoirs. The key takeaway is that perfect efficiency, converting all heat into work, is impossible because the cold reservoir can never reach absolute zero. This insight shapes how engineers design engines, power plants, and other energy systems. Thermodynamics powers many modern technologies. In power plants, steam turbines convert heat into electricity using thermodynamic cycles. Air conditioners use refrigeration cycles to move heat from inside to outside, requiring work input. Rocket engines demonstrate energy conversion by producing high-temperature gases that expand and create thrust. Solar thermal systems concentrate sunlight to generate heat for electricity production, maximizing efficiency within thermodynamic limits. These applications show how understanding thermodynamics leads to better, more efficient machines. Thermodynamics is the foundation for understanding all energy transformations in nature and technology. From engines to living organisms, these laws apply universally. Energy is always conserved, but entropy naturally increases, meaning disorder grows over time. Perfect efficiency is impossible in real systems, but knowing these limits helps engineers design better machines and technologies. By grasping these fundamental principles, we gain a deeper appreciation for the world around us and the science that powers our daily lives.